Hey everyone, my name is Aaron. Welcome to my channel. In this video, I'm gonna show you how to create a maze. Let me show you what our generated maze will look like. This is what you will get in the end. Let me show you how. There are a couple of important things that you need to know about these mazes. The first thing is that they always guarantee that there is a path between any 2 points that you pick in your labyrinth, and there is always only one path between them. This is super important because later on, when we're going to populate the whole labyrinth with enemies, we are going to be sure that the enemies can get from point A to point B. We are building a tower defense game here, so at the end we have to ensure that the monsters, the creeps, can go through the map, right? And this map guarantees that to happen. Okay, awesome. Let's take a look at the source code, and I am absolutely not going to pretend that I wrote everything manually. Most of this is generated with AI. Namely, it was generated with Claude 3.5 Sonnet, to be very specific, and I encourage you to do the same as long as you understand what the AI gave you. That's very important. You need to check, verify, and make sure that it's correct. Okay, let's see how we begin. Let's just get this part out of the way. In case you're not familiar with this, Python is made of modules. Each module is a file. I know I made a typo in the labyrinth file name. I'll fix it later, don't worry about it. The point is, it should be a Y and then an I and not the other way around. Never mind. This module is a file, and when I execute my Python code, there is the module which is the entry point of my program, right? My program can be many modules, dozens of modules. The one that I actually started is the entry point, and the way I know it's the entry point is that this variable, _name, is set to _main. This is just a convention, okay? Just remember that this means this was the entry point. And then I create an instance of this labyrinth class, and I just show the maze. Let's see what happens when I create the instance first. I have a couple of parameters, the max columns and the max rows of the labyrinth, and the block size, which is the display thing. When I display the labyrinth, let me do that real quick. How big is each block, okay? And my labyrinth is going to be, other than some bookkeeping, and then I'm gonna have a wall color and a space color, that's fine. And my labyrinth is going to be a list of lists, okay? So this kind of needs a certain amount of thinking, but let me just show you this. As you recall, lists are just exactly what the name suggests, list of things. However, nothing stops me from having a list as a member of another list, right? Because lists can have anything. And then this one will have X, doesn't really matter, okay? And that means that in this specific case, my maze is going to be a list of lists. Each list is a column of the labyrinth, and in that list, which is the column, each element is a number. And by agreement, absolutely arbitrary agreement, 0 means free space, 1 means wall, okay? Now let's see how this whole generation happens. But before I show you the algorithm, let me show you something else. How do we actually do this? How do we generate a maze, okay? Let me tell you about this. To generate a maze, we fill the entire maze with walls, and then like little mice, we chew paths into this solid block of walls, okay? Imagine it like cheese, and then the mice are just biting these curvy paths into the cheese. And it's completely random. The mice have no idea where they are, so they are just making these holes. Or imagine it like an ant castle. If you've ever seen an ant castle, that's exactly what ants do. They just dig these holes, and then they dig side tunnels, and then they dig side tunnels into that, and it becomes this mess of paths, right? That's exactly what we are going to do. So the algorithm is fill the entire maze with walls, start from the first spot, make it empty, and then just start randomly going around until we stop, until there is no way that we can actually move on, okay? And then we go back to the last point, which actually had a possibility to go in another direction, and start in another direction, literally like ants build the ant castle, okay? Let's see what it looks like in source code. Here we go. So, first of all, this line in and of itself needs some explanation, right? So, we have this part in which we multiply a list with a number. What does that do? Let me see. A equals this list. What is A? It's just a list. What happens if I multiply it by 3? Look at this. I get a list with 3 identical elements, okay? So what multiplication does is just increases the size of a list. It's a very nice shorthand. By the way, if you do this and multiply it by 3, what will the result be? Make a guess now. 3, 2, 1, go. And what happened was the exact same thing was copied, right, one after the other, okay? So that's what multiplication does to a list. So this here means that I'm gonna have as many ones in a list, as many columns I have. So this is one column, right? But what happens to this list is it gets repeated again and again, as many times as many rows I have. So this list, that is my column list, is repeated as many times as many rows I have, in which I get exactly the structure that I have mentioned. Is just a very Pythonic and actually a pretty dense way of writing this down, okay? But so, again, just to emphasize, this one here is generating one column, and the entire expression is repeating that one column as many times as many rows we have. You might ask, why don't we do the same multiplication and multiply the entire list to be that many? Because multiplication increases the size of the list. It does not generate more lists. It just increases the size. So we need this for loop in order, and the list comprehension to generate that list in which every element is a column, okay? Brilliant. Now the next thing is a little bit tricky, and just to make sure that you know what it is, this one here is a tuple, okay? Tuples are in a certain sense very similar to lists. In fact, if you are just using them, you might never notice a difference. But there is one very important difference. Okay, let me show you that there is absolutely no difference between them. They both print the first element, which is perfectly the same thing. However, if I have a function that says something, okay, and it expects x, and I will say x.append 3. Okay, observe this code. What we did is we just created a list with 2 elements and a tuple with 2 elements. We print both, and then we call a function that receives my list as parameter and appends 3 to it. And then we print it again, and we do the same with tuple. Pretty obviously, the reason I'm doing this is that there will be a significant difference in the output, which is that the tuple cannot be appended. Tuples are read-only. Let me put it this way. Tuples are read-only. You cannot change them. In programming language, we call these immutable objects, but you can just think of it as read-only. So the reason that this doesn't function is that the list can easily be appended a new element, but a tuple cannot, okay? So let's just go with this. The tuple is a read-only list. Actually, the differences are a little bit more nuanced because of knowing in advance that this tuple will never be changed, Python can do a lot of things much faster with tuples. So if you know in advance that you never want to do anything to this list, it's immutable, you don't want to write it, then you can absolutely use a tuple and be much faster, which is exactly the case with positions. Because we know for sure that when we are starting to collect the positions that we go through in the maze, we're never going to change them. We've been in that position, we save it as it is, no writing operation happens, so that's why we use a tuple here. And tuples, just as lists, can be element of of a list, right? Why not? So here we do a stack where we put this tuple of 1 and 1. That is column 1, row 1, the beginning position. Why not 0? Because we need the walls to be around the labyrinth so that nothing ever gets out, right? This is not a labyrinth that has an entrance and an exit. This is a completely closed labyrinth. After the creation, you can add entrance and exit if you like, no problem. But by the beginning, it has to be bordered or walled, right? That's why we don't begin at 0, 0, but 1, 1. And the same principle will apply all along. Each time we have to take 2 steps, because if we only take 1 step, then we would eat into a potential wall. We always have to take 2 steps to leave room for every second line to be a wall, right? If this doesn't make sense, don't worry, you will get this as we progress on. And then what we do is we clear that starting position, make it a free space, make it 0. And then we take all the directions that we could have as tuples, again, because we are sure that they are not going to change. And this means -2 in rows, that is 2 to the left, 2 to the right, 2 up, and 2 down, okay? That's what the directions are, okay. And now we have this stack. What is the stack? The stack is the list of points, of locations, or positions where we already have been while we were chewing our way through the maze, right? Why do we need this? Because whenever we run out of possibilities while we are creating one path, one route, we need to go back to the last point that still has open possibilities, okay? Let me show you how this works, and then it will make perfect sense. This is a bit messy, but what I'm going to do is, in every step of creating the labyrinth, I'm going to show you the actual status of it. This will blink a little bit, okay? I'm sorry about that in advance. I don't have any proper solution to this, so just bear with me while it blinks. In the beginning, just like I described, we cleared the very first step, leaving the border around us. Next step, we took 1 step to the right. It was random. We could have gone down or we could have gone right. We couldn't go up or left, obviously, because then we would go out of the labyrinth. This time it happened to be right, okay? And the reason that there are 2 steps is that we skipped 1 line for the wall, but kept the path in between. Okay, we stepped right again, and right again. This is going to be a very long corridor, but eventually we turned down. This is all full random. Now we have 3 options. We can go left, right, or down, okay? Let's see what happens. This time we went left, okay? And then down again and right. This is how the zigzaggy nature of the labyrinth comes out. This time we only have 1 option. We can go down because we already been there. Can go left because that's already not already cleared up. Can go up because we would quit the labyrinth, so we only can go right, and that's exactly what happens, okay? Okay, now I'll just keep pushing the button until this path gets stuck, yeah? And we will cut there. Okay, here we go. So now this path, which actually became quite a long and complicated path, but now it came to a dead end, right? It cannot go anywhere. This was the last one where my mouse cursor is at, okay? It cannot go up because it's been there, neither left nor right, nor down. So this is it. Now we are completely stuck. What's the next step? The next step is start going backwards until we find a position which still has open possibilities. This time it won't take long, because if we go to the previous one, which was this point here, down, it still can go down. So that's exactly what's going to happen next in the next steps. Now we went back, nothing happened seemingly, because we went back to the previous position. And in the next step, as predicted, we went down. And now we have the first actual corner where you have to choose which way you go, right? And this will here either go left or right. Let me see what happens. It went down actually, and then to the right. Now it's stuck again, right? Because here all 4 directions are blocked. So we are gonna go back to the previous spot and then to the previous spot. That takes 2 closings. Still nothing happened, but now we know that we're back here. And now we can go left. So the next thing that's gonna happen is we're gonna go left here, which is exactly what happened, of course. Okay, let me wait until it gets stuck again. Yep, the next step, immediately it went up, so it's stuck again. All 4 directions are blocked. We're gonna go back and continue it from here. And this is how the actual choices happen in your maze. This is why you get to choose certain paths. And this is the entire algorithm itself, because whenever this runs out, it will take some time, but then we will go back eventually to this point and start here upwards, and then this point, or oh no, sorry, I think it will be this point, yeah. This point will go downwards, this point will go up, and so on and so forth, until the entire labyrinth is filled with paths, right? And now you can maybe understand why we need to take 2 steps, not just 1, because we needed to leave every second row and column to be a potential wall if we actually get the path around that wall, right? Okay, let's see again the code. Okay. So when do we finish the maze generation? We finish it when we run out of all the potential positions which still could have another possibility to go to. We all know that it began with the initial position. It's going to end with the initial position, but it doesn't really matter to us. What we do in the next step is we take the last one from the stack, the last known position that could potentially have another path, or maybe not, we'll see. And watch this syntax, this is very interesting. What happens here is, in the stack we have tuples, right? However, we are making the tuple, which we know has 2 elements, equal to 2 variables, not 1, but 2 variables, like a list, but without the square brackets around it, right? This actually means, let me translate this to you here in a comment. This actually means x is stack, yeah, exactly. X is stack, the top of the stack 0, and y is the top of the stack 1, okay? But instead of needing to issue 2 different instructions, we can do it in just one go, and this is super comfortable, very Pythonic, very elegant, and pleasing the eye, right? At least my eye, don't know about your eye, but for me it's very pleasing that we do this so easily, okay? And then what we do is, we take this directions list, which is a list of tuples, and shuffle it. Shuffle, not hard to guess, it just changes the order of the elements in a list, like you would shuffle a deck of cards, basically. And each time we do this, we get a new order. So now we go through all the directions in random order, because they have been randomized, and take all the possibilities, looking for something that we can make a free space, okay? And then we create the new x and new y, which is the current position that we suspect could have some more openings to go to, and see if in that direction it is possible to go, right? So when is it possible to go in a given direction? If it's within the labyrinth, so within 1 and the number of columns, and 1 and the number of rows as well, and it is a wall. So we are taking always this certain 2 steps, two blocks away, and we check if 2 blocks away from here, we actually have a hole or a wall. If it's a wall, then we can go that way, because we have not been there yet, right? And if it was a wall, then we make it a free space by just turning it into a 0. And what happens is, we need to make the intermediate block also a free space, right? So we are here, 2 blocks away from here, we clear this space and make the connection between the current position and the newly opened position. Obviously, it needs to be a path. This is why you saw that we always have 2 blocks cleared in one go. That's the reason. That's actually 2 separate instructions. And then this new position that we have just opened, obviously, potentially has more openings. It might not have, we don't know, but it has the potential to have. So we put it to the stack. And watch the double brackets. It could be a little bit confusing, but this inside here, this is a tuple, right? If it was square brackets, you would immediately recognize that it's a list. Well, it's not square brackets, it's round brackets. So it's a tuple. Nonetheless, it's still the generation of the tuple and nothing else. And then we pass it as a parameter, so we need the square brackets here as well. Okay, and then we break, because if in one step, one search, we found the potential path, we are done for that iteration, right? So we break here. And here is yet again a Pythonic thing, which is the for has an else. And the else is invoked after the for loop executed, and it never invoked the break. So this is typical for for loops that are searching for something. If they haven't found, then we just execute the else branch. What does it mean? If all the directions were blocked for this specific location, that means this location is dud. It's useless for us, so we just remove it from the stack with a pop operation. Pop is the opposite of append. Append puts something to the end of the list. Pop removes it from the end of the list. You can actually give it an index and then it removes that specific element. That's fine for now. We just use the last one, okay? And that's it. And that's all the algorithm needs to do. Really, it's what, dozen lines or something? Not a whole lot, right? So this is how the algorithm works. Let me show you again what this results. We begin from the top left corner. This time the direction was down, so we took 2 blocks down, cleared this block because it was not cleared yet, and then cleared the block in between the starting position and the first block we found. And we are doing, now we turned right, we did the exact same thing. So 2 blocks to the right and clear the in-between path. And you can trust this algorithm, this will generate a beautiful, perfect maze. So just to see the final result once more, here is our beautiful maze. If ever you're developing a game and you want to have a maze in it, you can anytime use this algorithm and just be happy. Thank you guys for watching. I hope you learned something. I hope you enjoyed the mental process of actually figuring out how to generate a maze. I am really glad that you were here, and I'm looking forward to see you in the next video. Bye.